Okay, welcome back, physics fans. Doing a ladder question here, and we have a ladder that's 10 meters long, weighs 80 newtons. It's resting by leaning up against a frictionless wall, and it leans against the wall pushes back because that's a reactionary force, and it is at an angle of elevation that's with respect to the horizontal of 60 degrees. If the coefficient of friction is zero point 0.4, how far can a 320 Newton person safely climb up the ladder? So we have the ladder in here in purple that I've drawn, and there's two forces when it sits on the ground. There's a normal force that's perpendicular to the surface, and a frictional force that's going along the surface to stop it from dragging. And just in case you didn't envision it, here's the wall, and here's the floor. Okay, it's sitting up there. And there's a person climbing up it, and we know his weight, and his weight is 320 newtons. We know the weight of the ladder, the force of the center of gravity of the ladder is 80 newtons. And so we have 5 forces acting on this ladder. 5 forces acting on this ladder represented by the 5 arrows. We choose the pivot point at the base so that we get rid of these two when we have to calculate the torques. They still exist, but not in the torque calculations. So I'm going to start first with the sum of the forces in the y. So the forces up equals the forces down. That's where I went to and then decided I should record this. So the forces up, there's only one force up, and that's the normal force. So I'll leave that as just n. And the forces down, there's a force of center of gravity and a force of the man. And I chose nice numbers, 80 newtons and 320 newtons. Okay, so the normal force is going to be 400 newtons. Okay, now some of the forces in the x direction also have to equal 0. That means the forces left have to equal the forces right. So the forces left, the only one that's showing left in this, there's only 2 more forces that we haven't talked about, and that's the frictional force and the wall force. So the forces left, the frictional force, has to equal F of the wall. Now the frictional force, the formula for that is mu n, and that has to equal F of the wall. And we have mu and n now, 4.4, and the normal force is 400 newtons. F wall. So F wall is a number that we have already, and that's going to equal 160 newtons. Okay, scrolling up, trying to. So now we're going to do the sum of the torques. We're going to do the sum of the torques equals 0 when the pivot point is at the bottom. Okay, so the torque counterclockwise has to equal the torques clockwise. Now the torque clockwise is the F wall, because that's causing it to go around the pivot point this way. And the two other ones, the guy and the ladder, go the other direction. So this is the torque of the ladder plus the torque of the man has to equal the torque of the wall. That's going to be force times distance times the sine of the angle plus force times distance times the sine of the angle equals force times distance times the sine of the angle. Now the angles are what we're going to have to figure out. So I'm just going to zoom in here. Let's go to 300%. Stupid amount. Let's just zoom in here and figure out these angles. We're told that this angle here that's in yellow now is 60 degrees. Okay, that means this other angle here, Neither of these angles are used particularly because that's the angle to the first of friction and the angle to the normal, which are not in our formulas, but these are very helpful, having 30 here, because this makes this one 30, because alternate interior angles, and this one has to be 30, and alternate interior angles with the 6. So this guy has, this angle here with the wall has to be 60. Those are important. Okay, and again, if you don't get those angles, this is it. Just try to picture it. There's our pivot point. That's the radial arm to the guy. This is the force of gravity down. And we need the angle between the blue and the green. And you can do 150 if you were really desperate. It's easy. You could say that's the angle between them. And that's 150. And the sine of 150, though, is the same as the sine of 30. So it don't matter which one we use. Let's get out of there and bring it down to 125. I think that's where I was. So the ladder is 320 newtons. No, it's 80. 80 newtons. And it's halfway up the ladder. Okay, halfway up. So 1/2 of the 10-meter ladder times the sine of 30. I'm going to change color now to do the guy. The guy is 320 newtons. And we have to multiply it by the distance, and we don't know that distance. That's why it's going to be an x. That's what we're trying to find out. And we have to multiply that by the sine of 30. And I'm going to go to the equal side, other side, and that's the force of the wall, which we have. The force of the wall is 160 newtons, times the distance, which is the full length of the ladder, 10 meters, times the sine of 60. Okay, I'm going to bring that over up here. And we get the sine of 30 is 1/2, and 1/2 of 320 is 160. So 160x is going to equal, and that's going to be 1060 times the sine of 60. So 160 times 10 times the sine of 60 is 1385.64. And then this torque has to be onto the other side to subtract it, so we have to subtract it. And the units for that is Newton meters, by the way. And the other one is 1/2 of 10 times 80. Okay, so 10 times 80 is 100 times 800 times a half is 400, and the sine 30 is another half, so that'll be 200. So the torque caused by the ladder is 200 Newton meters. So we have to subtract 200 Newton meters from here. And then now we just have to solve for x. So we take this number, subtract 200. That'll be the total torque that is the person. And divide that by 160. And we got x is equal to 7.410 meters. Is that okay? Good question. That's how high up he could go to the ladder. Any little bit higher, explain what happens. If he goes a little higher than that, yes, he slips out. Why does he slip out? What's the physics that happens when he goes higher? Going down, the normal force doesn't change. Okay, true. As he goes further up, as he goes up, his torque increases. his torque increases, but the sum of the torques should be zero. That means the ladder torque stays the same. He increases his torque. That means the wall torque has to increase to balance. If the wall torque increases, which it has to, that means F wall has to increase. So in other words, the ladder ends up pushing more on the wall. As he goes up, the ladder pushes more on the wall. Therefore, the wall pushes back more on the ladder. And the sum of the forces in the x direction can't hold it anymore. The frictional force is actually smaller than the wall force. The sum of the forces don't add up to zero anymore. We get a net force, and a net force causes acceleration, and that guy is coming down. That ladder's moving away. Nasty. Anyways, thanks for watching. Remember, smash that like button and subscribe often.